Hello, welcome to chapter 2. In this chapter, we will be looking at motion in one dimension. That means motion along one line, so we don't need to consider two different directions like east-west and north-south. We will just take any one direction, let's say east-west. We might call it the x-axis, okay, for convenience. But it could be in any direction, it just needs to be in one direction, back or forth. So we're going to define some quantities to be able to describe our motion. And the quantities that we wish to define are these three quantities here: displacement, velocity, and acceleration. All three are what are known as vector quantities. And in the next section, we'll begin to understand what are vector quantities. But let's first look at displacement. Okay, so this describes the position of the object. When we study something in motion, we're really studying a branch of physics which is called dynamics, as opposed to statics. Statics, where something is stationary, and dynamics is when something is moving. Now, in dynamics, you could study several things. You could study why something moves, but we're not going to be concerned with that here. We're going to be concerned with mostly describing the motion. Okay, that portion is called kinematics. So kinematics is about the description of the motion, which means if we know its position and velocity at a given time, can we say something about its position and velocity at a later time? Can we say anything about the acceleration of the object? These kind of questions, okay? So if you consider position, and remember I said we're going to look at displacement, and displacement is related to the position of the object. We have to say, give a position with respect to some kind of origin, or with respect to something that stays stationary. We call that a frame of reference, okay? So simplest frame of reference might be just a set of coordinate axes, like you are used to the x-axis, and you need to define where your origin is. Then if I say something is 10 units to the right, you know, 10 units to the right of what? To the right of the origin. Or if I say it's 10 units to the left, then it's 10 units to the left, it's negative 10 with respect to the origin. Okay, so we need to define that origin, and we need to define our axis. Then we are set up to give a unique position. Okay. So if an object on this line, the x-axis, changes its position from some initial position, which we might call x0, 0 being for time equals 0 at that initial place, to some final position, xf for x final, okay, then the displacement is given by its final position, and you need to subtract out the initial position. So it's always x final minus x initial. Sometimes you might see this written as x subscript I for initial. Sometimes it's x subscript O for origin, okay, or the origin of the motion. And since it's a displacement, it's a delta x, which means a change in x or a change in position. This delta x is the displacement, okay? It's the change in position. So since the position might be in some units of length, for example, meters, then in the SI unit, our displacement is going to be also in meters. Yeah? So we might be at a final position of, let's say, 12 meters. And let's say we started at 10 meters, so we have a displacement of 2 meters. Okay. The displacement of an object is not the same as the distance it travels. For example, if I throw my pencil up and down, then it started in my hand, it went up, and it came back to my hand. So its starting and its final position are the same. So if I do x final, which is in my hand, minus x initial, which was also in my hand, we're going to get a displacement of 0. There has been no displacement. However, the object has traveled a significant distance. It has traveled all this way up and all this way down. We call that sum of the actual path traveled the path length. Okay? So there are several terms that might be important to distinguish at this point. For example, you might want to find the distance between 2 points, and this would be the mathematical formula. If you have a point xi, yi, which are your initial coordinates in 2 dimensions, and xf, yf, your final position coordinates, then the distance between your initial point and your final point is given by this mathematical formula. Delta S is the distance between them, not the displacement. Okay, remember, the distance is the shortest line joining these 2 points, right? That length. So that's going to give you the magnitude of the displacement. It doesn't tell you the direction. Okay, it doesn't tell you which point was initial, which point was final, since these terms are squared. So, but it does tell you the magnitude of your displacement. Now, the path length in the case of, for example, the pencil going up and down, or the ball thrown up and down, the path length depends on the actual route. So it might have gone vertically up and vertically down. That's twice the distance, right? So the path length is again different from the distance between the lowest and the highest point, right? And we saw earlier that the displacement was 0 in this case. So 3 things. We have learned displacement, right, which is final position minus initial position, okay? We have learned path length, which is the actual length traveled, okay, the entire distance. We have learned a distance formula, which is the shortest line joining any 2 points. And this distance is the same as the magnitude of the displacement, okay? So let's do some examples. Let's say here is your x-axis, okay? And we need to locate the origin. Here's the origin. It's been marked in units of 10, so we have 10, 20, 30, so on going to the right. These are positive. And going to the left, we have negative 10, negative 20, and so on. And it's given to be in meters. Here's a car at some initial position, which is written as A, and it moves from position A to a final position B. And if you had a better scale, you would see that the position B is actually 52 meters and A is exactly 30 meters. So it's not possible to read that off here, but just take these as given. So we know the initial position, we know the final position, which means we can find the displacement. Remember, displacement was final minus initial. So I'm going to have 52, take away 30, that leaves me 22 meters. That means I have a positive number, 22. So the displacement is positive, means it's a displacement to the right. Yeah? My final position is a greater positive number than my initial position was. Okay, so now we see that the displacement has a magnitude, which means the value, which is like 22 meters, okay, or 22 units, and that it has a direction. It's a positive number. So the displacement was to the right of its initial starting position, which is indeed the case. B is further to the right from A. Okay. Let's take another example where we have a negative displacement. So here we have a car starting at C, goes through D, E, and ends up at F. So this is my final position. And if you read this off, this is negative 53 meters. So this is going to be my final position. And the initial position here is C, which is 38 meters, okay, positive. So what is my displacement? My displacement is xf minus xi, so negative 53, subtract 38. It's going to give me a greater negative number, so it's going to give me negative 91 meters. So my total displacement is this distance, C to F, which is 91 units. And it's negative because it's to the left. My final position is a greater negative number than my initial position. Okay, so I have a displacement of negative 91, where this is the distance and this is the direction. So you see I have 2 parts to displacement. I have something giving me the magnitude, which is the value 91. I have something telling me the direction, which is the negative sign, saying the object moved to the left. So here we get introduced to a vector quantity. In the previous slide, we had a positive 22. So 22 was our magnitude, and the positive was telling us the object moved from A to B to the right. Yeah? So displacement is a vector quantity. Okay. And here we're just showing those combined motions, A through F. So remember, the car started at roughly 30, it moves to the right, then it reverses from C, D, E, F at some point. We haven't exactly seen it move from B to C, but you just have to assume that that happens, okay? That very same motion is here. This is the same graph, just in small. And we're going to actually plot this graphically, this information. So when you're asked to plot something, you have to carefully consider the axes. That's one of the first things you do. You want to look at what's going to be on the x-axis of my graph, what's going to be on the y-axis. And for now, we're just going to look and understand the relationship between this drawing, this sketch, and this graph. So on here to the right, in the x-axis, what would be our horizontal axis, we have time. So we're going to say that you move from A to B in 10 seconds. All these positions are 10 seconds apart. So 10 seconds from A to B, B to C, C to D, and so on. So every 10 seconds, we have a position. Yeah? We start at our time 0. That's our initial position. And what does this axis tell us? On this axis, we're actually going to mark its position in the x direction. So even though this is normally the y-axis, what it's showing you in this graph is the position of the object along the x-axis. Hence, we call this x meters, okay? Those are the units. It's starting at 30 meters. So at time 0, the car is at 30 meters, which is right here. And this is our position A. 10 seconds later, it's at B, which is at 52 or 3, I forget. And that on this graph would be up here. This is roughly 52 maybe, or 53. And that's our position B. At time C, it's at 38 meters, which is also positive. So just below 40, we have it here at C. Another 10 seconds later, it has moved exactly to the origin. So D is at the origin. Yeah, time is 30 seconds from the start. At 40 seconds, it's at E at just maybe negative 38 or so. Oh, here it shows you, sorry. Yeah, negative 38, which is here, E. And then at F, we are at negative maybe 53 or something like that. I forget that exact number. You need it from a more detailed scale, which is shown, not shown here. Okay, so this is F. So now we can understand what the graph on the right is. The graph on the right is what's called a position time graph. The position going on the y-axis, time going on the x-axis. So if I refer to a graph by a name, which will typically have 2 words representing the 2 axes, we'll always say the y-axis first. That's convention. That may be contrary to how you are used to thinking, because usually when we write coordinates, we write the x-coordinate and then the y-coordinate for a point. But when we talk about a graph, we talk about its y-axis and then its x-axis. So I'm going to show you the position, how it changes with time. Yeah, that's what this graph is. It's called a position time graph. Okay. And we'll stop here for this section. Thank you.